All right, so hello everyone, thanks for coming in. This is Flow, a seminar series on federated learning, broadly construed. So if you've been sort of active or participating in Flow before, you already know that we essentially cover ML, distributed optimization, privacy, crypto, sort of systems aspects of federated learning. And before we start with Chris's talk, two quick admin things. So probably you've seen that the meeting is being recorded. And second of all, if you have questions during the talk, since the speaker cannot hear us, you have to write into the chat. And we're
okay, I fixed it. I can hear you now.
Ah, okay, all right. That's much better. Okay, so that simplifies things. So if you're a spectator and you have questions during the talk, please write them into the chat or raise your hand and we will unmute you and you can ask the question live. So yeah, and without further ado, let me introduce Chris Desan, who graduated from Stanford in 2017, where he was advised by Cornell and Chris Ray. And he's currently an assistant professor. Like since graduating, he's been an assistant professor in the computer science department at Cornell. He's a member of the Cornell ML group and where he leads the Relax ML lab. His research interests include algorithms, software, and hardware techniques for high-performance machine learning with a focus on relaxed consistency variance and stochastic algorithms such as asynchronous low-precision SGD or Markov chain Monte Carlo. And he's also been very active in the sort of federated learning related topics. And this is, I believe, what he's going to talk to us today. So take it away, Chris.
Great, thanks for the introduction. And yeah, today I'm going to talk about some ideas relating to distributed and decentralized machine learning. So federated learning is one of the, if not the main sort of application for this type of work, but the work is a little bit scoped a little bit more generally than that, and we'll kind of get into that. And on a high level, this is mostly a talk based on the paper Optimized Complexity in Decentralized Training from my student Yucheng Liu, who's pictured here. So, much of the credit needs to go to him. There's been this really great line of work that he's been working on decentralized learning and on some great theoretical results, which we'll get into in the talk. So just to give an overview or a motivation, right? Why do we care about this? Machine learning basically refers to programs that get better with experience, by analogy to how humans also get better as we get more experience. And the consequence of this is that because more data means more experience, if we're able to build a system that is able to process more data, that's able to learn from more data, we can actually often learn better. And this means that in machine learning, systems improvements lead to better services. So we have a whole decade of improvements in machine learning, from object recognition to speech recognition to reinforcement learning, that are built on top of systems advances that allowed us to learn from much larger data sets. And so my main research interest is how we can make machine learning systems better, how we can make machine learning more scalable, how we can make it more reliable when we scale. And as a result of, partially as a result of these types of systems improvements, the scale of representative deep learning applications has been, dramatically increasing over time, exponentially increasing even. And as we've seen the scale of these applications increase, we've also seen a corresponding improvement in the performance of the application and the accuracy of the application and the sort of utility of the models that we train from these data sets. Now, one way that we can support this type of large-scale training is through the use of distributed learning and decentralized learning. And really, distributed learning is just exactly what it sounds like. You have, rather than one machine that's doing the learning, you have n machines, some large number of machines that can thereby process more data than they would be able to do if it was just one machine. That's very natural. And decentralized learning takes this a step farther and says we also want to remove any central bottlenecks to the system. So for example, if I had a single machine that was maintaining the model that all the machines were learning, that could be a bottleneck for training. And so decentralization says, let's eliminate that and use some sort of algorithm that has no centralization, no single point of failure in the system. And there have been dozens of papers on decentralized learning over the past 6 or 7 years since it really started being a popular thing. And these have kind of gone along with the scaling of deep neural networks, although not all deep neural networks that are running at the largest scale are based on decentralization. There are also a lot of viable methods for scaling centralized machine learning. So, decentralization is really cool, not the only way we scale, but still a major research area. But okay, to start out, before I kind of get into what centralization is, I just need to talk about how we distribute in the first place. There's a question: what are other ways to scale learning instead of distributed learning? This is a good question. There are a couple of things that we can do. So one thing that maybe is straightforward to do is to just, rather than distribute, you just use a single machine that is large and sort of beefy. So use better GPUs, use multiple GPUs, use multiple CPUs on the same computer, and then just kind of wait longer than you otherwise would be able to do that. That's really the option. That's really the alternative to distributed learning. And sort of the other classical alternative is supercomputing, which we don't see as much use in machine learning, but which is an alternative. But for the most part, if you want to scale up to largest scales, you're kind of forced to use distributed learning. At some level, it's the only game in town.
Thank you.
Sorry, go ahead. It sounded like someone was saying something. Maybe not.
I think they were just thanking you for your answer.
Oh, great. Excellent. Okay. So to start out with, before getting into what decentralized machine learning is, I have to talk about what centralized machine learning is and what the sort of classic paradigm for distributed learning that we're talking about is. And really, this is a central common paradigm supported by essentially all modern large-scale machine learning systems. And the idea is that you either have some sort of parameter server set up, or you have some sort of AllReduce style setup where all the workers are communicating and are computing basically just regular stochastic gradient descent. And they're doing that by parallelizing over the batch dimension. So in other words, in classical centralized SGD, all the workers work together to compute something that is numerically equivalent or computationally equivalent to if we were to run SGD on a single machine and just wait for a longer period of time. And really the two most common ways of doing this in the distributed setting are the parameter server method, where there's a single server called the parameter server that maintains the current sort of gold standard copy of the parameters, the most recent copy of the parameters. All the other machines are so-called worker machines. The worker machines compute gradients. They send those to the parameter server. The parameter server updates the model, updates the parameters, and then sends those back to the workers. So this parameter server style setting is typical of federated learning. In applications in the data center, we also often see an AllReduce style pattern, wherein we use something that is equivalent to maintaining the model on every worker. Every worker computes gradients. Every worker then sends the gradient that it computes to every other worker, which then performs the SGD update essentially in a way that's identical across all the workers. So they're just summing up the same gradient vectors, producing the same value of the model. And in this way, all the workers basically have the same parameter vectors in lockstep. And even though they redo some of the work, so the work of summing up the gradients and updating the model is repeated, it can still run pretty fast because that's not the dominant factor in the system. And of course, both of these methods are unified by the fact that they're computationally equivalent to just regular SGD. They're equivalent to running it on a single machine and just waiting for longer. There are some more sophisticated methods that some methods use and that really are used in practice. So for example, the AllReduce method that I just wrote on the previous slide is not really what people run in practice, because actually doing pure all-to-all communication across a fully connected graph is expensive, because you need to send an amount of data that is proportional to the square of the number of workers. That can become expensive when the number of workers becomes large. So for these very large scale tasks, most companies will drop to something simpler, like using a ring AllReduce strategy, where the accumulation of every gradient at every worker is done by communicating in a ring, where, for example, the gradient from the first worker would be sent to the second worker, which is then accumulated and sent to the third worker, which is then accumulated with that worker's gradient and sent to the fourth worker, etc. Eventually, all the workers get all the gradients. And so this is how it's typically done in practice. But the main point here is that this is still equivalent in terms of what's being computed to what we saw on the previous slide. So, okay, that's what people are doing. Let's try to formalize it a little bit more, because eventually we're going to be stating some theorems in this talk. And so we need to understand really formally what we're doing. And here, when I say, distributed decentralized learning, what I really mean is distributed decentralized optimization or stochastic optimization. So what we're really doing is we're trying to minimize the sum of the losses on a bunch of workers, where each worker has some local data set, which I'm denoting D sub I, and so what we're trying to do is to minimize the sum of these losses. And you can kind of think of this as the whole training set has been somehow partitioned over all of the workers. In federated learning, for example, each worker or each learner has its own set of data. And then what we're trying to do is minimize the loss over the whole data set consisting of all data from all of the workers. Okay, and we can express this as an argmin problem. And what we're going to do is we're going to adopt sort of the classic assumptions that we make when we're studying optimization. So I'm going to assume that the loss function is smooth. I'm going to assume that the loss function is bounded from below. And we're going to need to make some additional assumptions, but these are the only assumptions that we would need in order to prove that centralized, non-distributed SGD converges if we were just running on a single machine. So any additional assumptions past the slide are going to be ones that deal with the distributed and decentralized nature of the problem. Sorry, past this slide. We still need some assumptions about the examples. So here we just assume smoothness, and we're also going to assume that the functions are not too different from each other, the individual component loss functions. for the different elements of the data set, so that we can, by subsampling, which is what we always do in large-scale stochastic gradient descent, we can produce an estimator that is not too far off from the full gradient. And so that's all we're doing. We're assuming that we have some first-order gradient oracle here that in expectation is the full local gradient, and that has some bounded variance, some bounded squared error. So that's the setting, that's the problem that we're trying to solve. And we've kind of already seen, or at least I've shown you some examples of what centralized SGD looks like. And now I want to go into kind of what it means to be decentralized, because I haven't really defined this term yet. And what was interesting when we set out to work on this project, one thing that we discovered in the course of doing a literature search is that different papers actually use the word decentralized to mean different things. And we saw roughly 3 ways in which the term is used, which refer to the system being decentralized at different layers of the computation. So we can either have the data be decentralized, we can have the communication protocol, or the communication algorithm be centralized, or we can have the network topology itself being decentralized. And I'll give you a sense over the next few slides about what these different notions of decentralization mean in this context. So centralized data, the classic setting, really involves some centralized storage of all the data. So maybe we have some heterogeneous data sources, but they're all stored on the cloud, or they're stored on some disk, or they're stored in some data warehouse. And they're then sent to the workers after being shuffled. So essentially, each worker's data is equidistributed with each other worker's data. Or maybe if they're not equidistributed, they're close to being similarly distributed. So we can say that the distributions of the data sets on the different workers are close to each other. And to decentralize this, we just remove the centralized data store. So we say we might have some data sources. The data sources are heterogeneous, but we're not going to care about that. We're just going to assign each worker some data. Whether that data is the same on the different workers, we won't care. And you can see how this is better from a systems perspective, because it means that we don't need to centralize the data. We can avoid that compute stuff. We can avoid that storage step. And it's often the case that in applications, and federated learning is the main application that has this property, that the workers are in some sense the same as the data sources. So in the classic example where the worker is a cell phone, the data is coming from the cell phone that's actually doing the work. So in some sense, this is a very natural way of computing, but it means that we work without this shuffle data property. And in particular, when we look at theory of decentralized SGD, the difference between theory for the decentralized data case and the centralized data case is that in the centralized data case, it is reasonable to make an assumption that there's somehow low variance between the different loss functions on different machines. So if Fi is the loss function on the ith worker, then the squared error between the gradient of Fi at any point x and the gradient of f, where f is the full loss function, is bounded from above by some constant, and this constant is independent of the number of workers. This assumption is reasonable to make in the centralized data setting, where we can replace this variance with something that depends on the variance of the data in general. But this type of assumption is something that we wouldn't have in the decentralized data setting. And we can distinguish some analysis of decentralized data and centralized data by whether they adopt this type of assumption. Okay, so that's what decentralized data looks like. The centralized communication protocol is actually, it's a very different thing that we're looking at. So here we're saying that centralization has to do not with where the data comes from in this sense, but centralization has to do with how the algorithm runs. So a centralized communication protocol is, in the most ideal setting, something that tries to compute something equivalent to what SGD on a single machine would have done. So the typical setup of this would involve a parameter server, and typical centralized communication protocols involve sending gradients over the network and sometimes receiving parameters, although sometimes we also only send gradients and don't send parameters at all. The sending of gradients is a central property of these centralized communication protocols. And in a decentralized communication protocol, on the other hand, we want to remove this property. So we're going to drop the requirement that the system be equivalent to what centralized SGD would have done, or to what single machine SGD would have done. We're going to also generally want it to be the case that no one worker needs to be aware of the whole system in the way that the parameter server needs to be aware of all the workers. And rather than having a single copy of the model, as in single machine SGD, and as in the parameter server case, we're going to let each worker have its own independent copy of the model that are allowed to diverge, where rather than sending gradients, a decentralized communication protocol is going to send parameter vectors and work by averaging those parameter vectors. And this is kind of capturing the general idea of what it means to be decentralized in this sense. But actually, when we look at how decentralization is used in the literature to talk about communication, they are usually talking about something more specific. So they say that decentralized communication is specifically the use of a particular algorithm called gossip, or the gossip protocol. And the gossip protocol has all of these properties, but it's a specific algorithm. So how does it work? Well, the gossip protocol works by averaging by multiplication through what's called a gossip matrix, which is a fancy term for a matrix that's doubly stochastic and symmetric and non-negative. And basically the way that it works is that if you imagine the models for each worker as being concatenated together in a matrix, so if the number of parameters is D, the number of machines is M, then this would be a D by M matrix. Then the averaging step corresponds to multiplying on the right by this matrix W, this doubly stochastic matrix. The reason why we want it to be non-negative and doubly stochastic is so that this is a sensible averaging pass. And this was one of the sort of first successful decentralized protocols, DPSGD from 2017, wherein just what they do is that they run in a loop. At each step, each worker computes a local gradient. It then averages its parameters with its neighbors using a gossip matrix, and then updates its parameters. And then the workers all synchronize. And they showed that this converged under the assumption that the gossip matrix has a second eigenvalue that is bounded away from 1. One thing that we would note about this setup is that the gossip protocol could be made to be equivalent to centralized SGD if we used a matrix where every entry is the same, right? So if every entry of the gossip matrix was 1 over M, where M is the number of machines, then that would be exactly equivalent to running AllReduce. So when we talk about gossip, we're typically excluding that case and just considering cases where the gossip matrix conforms to the sparsity structure of the communication graph of the machines. So in particular, in in this network topology, where the machines are connected to each other in a sparse way, then for our gossip protocol, we would require that the entries of the gossip matrix corresponding to connections between machines that aren't connected to each other in the network are 0. And in that case, we can effectively compute the multiplication by the gossip matrix and compute this gossip averaging step by just having each worker communicate with its immediate neighbors. And this notion of communicating with its immediate neighbors leads directly into the notion of the network being decentralized. So in centralized network topologies, we basically have a fully connected network. We have every machine connected to every other machine directly. And in a decentralized topology, this is sort of relaxed, such that workers are connected in some sparse graph, and each round of communication only lets the workers communicate with their neighbors. So you can kind of see how this is connected to the notion of gossip, but it's not exactly the same, because you could choose to run whatever algorithm you want, not specifically gossip, over a decentralized network topology, including running a centralized algorithm like ring AllReduce. So there's a question, is the step 2 in DPSGD happening only once? That is, there's only one round of averaging? So yes and no. There's only one round of averaging per gradient computation. But every time you compute a gradient, you also average. So the process is compute a gradient, update, average the models, and then update your own parameters using the gradient that you computed. And part of the reason why it's set up like this is so that you can compute the gradient and do the averaging in parallel, which is nice, overlapping communication and computation. But the averaging does happen multiple times, just only once in each step, only once per gradient step. There's another question. In the more general decentralized communication protocol you're considering, is the graph still sparse, not fully connected? Yes, the graph is pretty much always going to still be sparse. If the graph is fully connected, then the gossip protocol doesn't exactly make sense. Typically, we would only talk about the gossip protocol in the context of what? Sorry, there we go.
Yeah, I don't know, I was on mute, so I don't know if, sorry for the interruption. So yeah, I was talking about general, not the gossip for the fully connected. I was talking about, given that you mentioned that you want to go beyond gossip, so I was wondering whether what you have in mind, the communication, general communication protocol you have in mind goes beyond gossip when you have a not fully connected graph. Because you mentioned that you can decentralize any centralized algorithm going beyond gossip. So I was wondering, how can you do that if you are not fully connected? Unless you don't pay a lot in terms of communicating every time something of the order of the diameter.
Then typically the way that you would make it decentralized is by just kind of imagining that you're not. So you would use a gossip matrix that is sparse, and more sparse than the actual network that is backing it up, in order to avoid the expensive all-to-all communication, even though your network would be capable of the all-to-all communication. But in practice, it's rarely the case that you have a large-scale network where every machine is connected directly to every other machine.
Yeah.
So give me a minute and a half. I think my charger is broken. So I'm gonna go get another charger. And hopefully it is not my laptop that's broken. sorry about that. I didn't want my laptop dying in the middle of the talk. It was about to do. Okay, so through centralized network topologies, we can kind of think about what all these different notions of decentralization mean by looking at this table. So there are different layers of the system, the application layer, the protocol layer, and the network topology layer. And each one has a notion in which the system can be centralized or decentralized. And these different notions correspond to different systems trade-offs and to different applications. So federated learning is a classic example where what we really care about is being able to support the unshuffled data, because centralizing the data is something that we generally wouldn't want to do for privacy reasons. And we can think of similar applications for decentralizing the protocol and decentralizing the network topology. And so what we want to do here is we want to understand the theory of fully decentralized learning algorithms, fully decentralized optimization. But we're going to start with just reasoning about decentralizing the data and the network by themselves. And the reason for this is that the gossip protocol is actually fairly restrictive. It'll be easier to design algorithms and to understand lower bounds without making assumptions about how gossip is being used. And then after we do that, we'll see what happens when we add gossip back in. So here we're just in the decentralized data, decentralized network topology. And to understand how we might achieve the optimal rate and how we might derive what the optimal rate is, let's understand what the classic centralized approach looks like here. So each worker is going to get a copy of the model. And if we imagine that we're looking at the sort of common case where the communication graph is a ring, like illustrated here, basically what we do is we have each worker query the gradient oracle, each worker computes the gradient. Then there's a traversal of the graph, and it actually takes 2 rounds of traversal because you need to get the average gradient and propagate it out to all of the workers to basically compute the sum of the gradients. And then all the workers can use that to update their own copy of the parameters by basically replicating the same computation. And the natural question is this ring AllReduce really the best solution? Well, imagine that we were to do something more general. So let's say that we're allowed to query the gradient oracle at most b times total. B here really represents our mini batch size. We imagine that we're allowed to now, rather than doing the ring AllReduce, we can do any sort of communication, but we're only allowed to do the communication over this communication graph. We then imagine that there's some update to the model parameters, but that we're only updating the model parameters based on gradients actually from the system. So we're not like using some oracle from outside the system to change the parameters that are set. And then that the algorithm returns any model or maybe any combination of the local models on each of the machines. So we're trying to derive a class of algorithms for which we can then prove a lower bound, because in order to understand what's optimal, we first need to get a lower bound. And so here concretely what we're thinking about is we're thinking about a class of functions, the functions basically that are smooth functions with lower bounds. We're thinking about gradient oracles, which have bounded variance and are unbiased. And we're thinking about algorithms that have a bounded query budget at each step that can at each step send and receive with other workers in their neighborhood, and the things that they can send and receive are just gradients and parameters, and where you can only have gradients from the system that are actually being used to update the parameters. So like no clever out of system thing. They're running something that is essentially a gradient method or stochastic gradient method. And then here, what we can conclude is that what we want to know a lower bound on the sort of class complexity of this algorithm. So we're looking for the smallest time, the smallest number of steps t, such that in expectation, the gradient of the full loss after t time steps is smaller than some target error epsilon, right? And we call this the time, or the class time for algorithms in class A, oracles in class O, functions in class F, and graphs in class G, where G is a set of graphs, F is where G is a graph, F is a function, O is an oracle, and A is an algorithm. And then what we're interested in is a class bound. So what is basically the worst case number of steps that we would need to guarantee that the gradient is small over some class of functions, some class of oracles, some algorithms, and some class of graphs. And okay, this is kind of the first theoretical theorem statement in the talk. So what we showed is that if we're looking at the sort of best rate that we can get by minimizing this amount of time over algorithms, so we want to choose an algorithm in the class that gives us the best time, then that time is bounded from below by basically delta L sigma squared over NB epsilon to the fourth plus delta LD over epsilon squared. And we can unpack this as basically delta L are functions of basically they're function parameters. They have to do with the smoothness of the function. Sigma squared is a variance parameter. N is the number of workers. B is the gradient budget, so the number of times you can query the oracle on each machine at each step. And epsilon to the fourth is our gradient error tolerance. Then we have a second term that depends on the graph parameter and scales as epsilon squared. And really what this is saying is that you depend on both statistical properties of the function and properties of the graph, but they sort of have different dependencies depending on how small you want epsilon to be, how small you want your error tolerance to be. And in machine learning, we usually don't take that error tolerance to be all that small, so both of these terms could be important. And in particular, what this shows is that there is a real dependence on the graph diameter, such that as the graph diameter becomes large, the number of steps that you are going to need to run will also become large. And this is natural because as the graph diameter becomes large, you need to take more steps to even communicate between any pair of examples in the graph. And note, this is just a lower bound in general for all algorithms, not just for centralized algorithms and not just for gossip algorithms. And so, okay, how can we achieve this theoretical lower bound? Well, actually, kind of the naive algorithm works. So what you do is you build a spanning tree of the graph. You then just run essentially simulating centralized SGD. So we query the gradient oracle B times. We accumulate gradients to the root by communicating through the spanning tree, and then we send the average gradients back. And this is going to take a total of 2D steps of communication to do. And so just by the kind of straightforward setup, the analysis here is going to give us whatever the rate for just single machine SGD is, which would be delta L sigma squared over NB epsilon to the fourth plus delta L over epsilon squared. That's the rate that just single machine SGD gets. And it will result in that multiplied by D, because each step of this algorithm requires D rounds of communication. And okay, is this optimal? Well, no, it's not. And the reason why it's not optimal is that this first term doesn't match. It has an extra factor of D, but okay, we can get rid of this by adding more gradients. So we're basically effectively increasing the mini batch size. So each step of this outer loop, rather than querying the gradient oracle only b times, we query it db times. And this is enough to sort of eliminate this rate and get or eliminate this factor of d in the first term, because you're effectively multiplying b by d, and get basically an optimal rate, which is pretty cool. But okay, this algorithm is a little bit silly, so we want to understand maybe a more general communication algorithm we can use. And one way that we can do it is we can say, well, what we really want to do in general is we want to do this with averaging, not with just direct communication. Because in the previous step, we were thinking about sending gradients along the tree. That can be expensive, require a lot of bookkeeping. If we can do this with averaging, that would be better. And we can. And so the way that we do this is we use this lemma that says that if what we want to do is we want to factor a matrix that's the all ones matrix, which is basically this all ones over n matrix that's equivalent to just computing AllReduce. We can do that with a number of averaging steps where each one of these averaging matrices is a doubly stochastic positive. Actually, is it positive? Is it certainly a doubly stochastic matrix? Such that the product of these matrices is this averaging matrix. And so then what we can do is we can replace this with this simpler setup where rather than communicating by a spanning tree, we use these factor matrices as averaging steps. So in our outer loop, we still have this d times gradient oracle computation, but then what we follow it up and do is we communicate via multiplication by these factor matrices, and that's basically equivalent numerically to what we had on the previous slide. There's a question, if the graph is given, can I always find such R matrices matching the graph sparsely? So the answer is yes, you can. I think that the task of finding a minimal R is potentially hard, but certainly finding a reasonable R that's less than 2D is very easy. And in fact, the lemma is constructive, so it gives you a way to construct the matrices. Another question, in algorithm 2, we consider send or receive gradient as one message. Some real physical media allow performing broadcasting of messages physically with the lower bound change in terms of dependence in B. So here, sending and receiving gradients is one message. And in fact, one messaging step consists of every worker sending something to its neighbors. So one message involves communication along every edge of the graph.
So broadcasting is out of scope of this analysis. So what's your opinion?
So if it's broadcasting to every worker in the machine if it's broadcasting to all the workers in a single step, then that would be out of scope here. That would be corresponding to a fully connected communication graph. If it's just broadcasting wherein each worker sends the same message to everything that it's communicating to, that is essentially what we buy by having this averaging step. So the workers' messages are actually averaged with this algorithm. Are actually broadcasted with each algorithm. Are actually broadcasted with this algorithm in the sense that every worker that it sends to is being sent the same message, but it's not being sent to all the workers in the system.
Okay, thank you.
And that's one of the things that this averaging protocol matrix factorization setup buys you. Okay, so we're almost there. And in some sense, this multiplication by matrices looks a lot like gossip, but it's not gossip. And the reason why it's not gossip is that we're not multiplying by the same matrix at each step, right? And also the matrices are required to be symmetric and positive, whereas these matrices aren't necessarily. So can we make this work in a fully decentralized setting by adding gossip? And okay, if we recall the theory for, known theory for the gossip protocol in DPSGD, here each worker is going to get a copy of the initialized model. We average by using the gossip matrix, and the rate that they get requires the assumption of centralized data, but they get something like delta L sigma squared over NB epsilon to the fourth, which is basically the optimal first term rate, but their second term is delta L n var sigma squared over epsilon squared times 1 minus gamma squared, where 1 minus gamma is going to be the spectral gap. And this second term rate is, as we're going to see, pretty bad. And also the fact that it depends on this centralized data assumption is also unfortunate. So how can we fix this? Well, what we're going to do is we're going to also prove a lower bound. And here our lower bound is going to be a now restricted lower bound where we're considering not arbitrary algorithms, but algorithms that use the gossip protocol. And here we can show that if we restrict to algorithms that use the gossip protocol with gossip matrix W, we get the same first term, but our second term is replaced by delta L over epsilon squared times the square root of 1 minus delta, where 1 minus delta is the spectral gap of the matrix W. And this is a similar bound to what we got before, but specialized to the gossip setting. And so we can immediately see that there's a huge gap with what DPSGD got, and subsequent gossip algorithms were able to close this gap a little, but not actually reach the optimal bound. So what we're going to do is we're going to try to understand what was causing problems with DPSGD. And the high level reason is that while we're communicating, the gradients are somehow computed on a noisy model that depends on aspects of the communication noise that haven't settled yet. So if we were to run multiple communication rounds, the system would eventually reach equilibrium, but it's not at equilibrium yet. And every time we compute a gradient on a worker, we're computing it not at the eventual equilibrium state, but we're computing at the current state, which is noisy. And we could solve this with additional communication rounds, but that would compromise the throughput because then we would have to wait for many more communication rounds. So what we're going to try to do instead is we're going to parallelize the communication with the backprop on two different model copies. So what we're going to do is we're going to do something like the following. Over a mini epoch length of R, we're going to compute a gradient on the model, and then on a separate copy of the model, we're going to run a gossip averaging step. And then only at the end of this R epoch are we going to basically take these gradients and add them back into the model that we compute. And there's a full algorithm statement in the paper. Since I'm running out of time, I won't go too deeply into it, but that's actually able to achieve the optimal rate, at least to within logarithmic factors, which is pretty nice. And not only does it do that, it outperforms a bunch of other centralized models in practice. There's a question, are you in fact using gradient tracking methods? Yeah, I think that what we're doing is similar to gradient tracking. Although it's not exactly the same. So
do you mind,
sorry
if I interrupt you, do you mind to elaborate on the difference with gradient tracking? What would be because gradient tracking have been used a lot in different variations, right? So, you say that this is not exactly gradient tracking. Can you just elaborate on the difference? Why, for example, why can you use gradient tracking if you cannot? Is there a caveat? Why do you need to do something different? I'm just curious because I know gradient tracking quite well. So I was just curious to see what does it work and what does not.
So here we are not. So the problem is that I don't know enough about the gradient tracking literature to actually be able to say how different it is from the simplest version, from this most close version of gradient tracking to what we're doing here.
Even if you play the vanilla gradient tracking, it's like a dynamic consensus. So you have a gossiping, but instead of just averaging the variable that you use to estimate the gradient tracking, you add the subtract your local gradient, the new iteration, and you add the gradient of the new iteration, your local gradient, you subtract the previous one, and that's the information you're going to share it. And this will converge to the average of all the gradients if the consensus is working. So it's like a dynamic consensus. Think of a gossiping, but
okay. So in this sense, you could use. Let's see. It's similar in that they both try to reduce the noise from gradient averaging, but whereas gradient tracking is using something that's kind of like momentum to do it. Here, all that we're doing is we're waiting for a longer period of time before sort of using the communicated gradients to before using the communicated models to compute new gradients. They're basically waiting for it to die down. And I think that the theoretical difference is that the gradient tracking stuff doesn't play nice with decentralized data, although that may have been fixed since we wrote this paper. But I think like D squared is in this class of things. I don't know, correct me if I'm wrong. You're probably more familiar with the more recent literature than I am.
Yeah, I know the gradient tracking literature, but I don't know how it fits in your general audience. So maybe we can talk offline. I will read your paper carefully. And maybe, we can. Thank you.
Well, okay. Cool. So takeaways. Main ones are, okay, there's 3 layers of decentralization, or at least 3 ways that we can think about decentralization. And the main contribution was lower bounds for these fully decentralized optimization algorithms and a algorithm that actually performs reasonably well in practice that matches the upper bound, which is pretty nice. All right, so I'm almost out of time. There's like a second thing that I wanted to talk about, which I will go through really quickly. No, actually, do I even want to go through it? Let's not. I was going to talk about low precision communication, but it's fine. We have an algorithm. Basically, the high level of this is that we have some algorithm that can also compress the communication between the workers when we do this. And if you're curious about that, then read, where is it? This paper, Moniqua, Modular Communication in Decentralized SGD, although to be honest, it's not the only paper that does communication compression in Decentralized SGD, and there's a lot of really good work in this space. But since we're running out of time, I'll just kind of conclude with a recap. So the whole point of this was that we wanted to make our systems more scalable. We want to make them run in parallel, and better systems are going to lead to better services. And so by making improvements at every layer of the stack, we can get better algorithms, and we can do it while also proving theory about them being optimal, which is really nice. And just to kind of conclude, I do a lot of other types of research. So I do statistical inference via Markov chain Monte Carlo, a lot of parallel asynchronous and distributed learning, learning with compressed machine learning and learning with low precision arithmetic, machine learning accelerator hardware, so hardware design, learning on manifolds, in particular learning on hyperbolic space on curved surfaces. And most recently, I've been looking into optimal example orderings, or at least better example orderings for SGD, kind of beyond the curriculum learning paradigm. So if any of this stuff is stuff you're interested in, I'd be happy to talk about it. And sorry for going a little bit over time. I'd be happy to answer any of your questions now.
I'm just checking. So, I mean, there is one sort of generic question I have, maybe coming back to your original motivation, or at least the connection to federated learning. I mean, what is kind of the system model that you'd like to essentially, I mean, to which you think these results would sort of best map to? Like, is it like some kind of federated setting, some kind of completely decentralized setting, something in between? Like, what would you think in terms of sort of practical
I think the results most apply to a setting in which the workers are physically like close to each other, and physically connected to each other via sparse topology that is roughly corresponding to the one that is being used in the network topology. Or equivalently, one where the workers are connected to each other via a traditional network, but where communication that's all to all is going to be, you know, intractable or just bad for the network. And so communicating over a sparse graph would be better. And I think that this latter thing is actually generally the case for networks running on or for applications running on the cloud, or even over like a traditional network stack, because you don't want to confuse the links, and you don't want to overburden any one link of the chain. You don't want to generate too much network traffic. So that's the setting that the theory most directly corresponds to. It would be interesting to look at this in the context of federated learning, but nobody, I think, has really looked at, or at least last time I checked, nobody had looked at like a totally decentralized federated learning. Pretty much all the federated learning systems I've seen have some centralized coordinator that coordinates all the work.
I mean, I believe that the word federated comes, it sort of would imply the equivalent, like the sort of the existence of some kind of centralized type.
Right. In the sense of federation, but
I do think that there was at least a project from Yandex where they were actually trying to build really sort of internet scale sort of AllReduce type things where I imagine you have a sparse overlay on top of which you're running some SGD type thing. So maybe that's a reasonable, reasonable sort of practical embodiment of something like this. But maybe, I'm sure that someone from that team would be better to sort of better at sort of checking this rather than myself. Are there any other questions? I think given that there are no other questions and you answered quite a lot of them during the talk, I think we're gonna end it here by thanking you again for a very, very nice talk. And
thanks for having me.
Thanks for sticking around, and see you all in the next flow meeting. Bye-bye.